All right, so you should see my screen now. So I think you probably already know who I am, but if not, I'm Eric. I work at UCLA on the SPEDAS team. And for the agenda, we're going to cover MMS data. First, we're going to go over ephemeris and coordinates, and then fields, and then the EPD instruments, that's FEEPS and EIS, and then the plasma instruments, FPI and HBCA. And a few notes at first. So everyone's muted by default, but feel free to unmute and ask questions anytime. You can also email me afterwards. My email is a couple places here, and it's also in the announcement email. And another important thing is that we're recording this, and I'm going to try to post it to YouTube later. So if you don't want your voice recorded, don't unmute. But of course, you can always email me questions after, and I'm always happy to help. And for detailed science questions about the data products, see the release notes for the instrument you're interested in, and then contact the instrument team. I'm mostly just a software guy, but I do have some general knowledge about the data products. So if you have questions about the data products, you can email me, but I might not know the answer. I might have to forward you to the instrument team. And if you don't have their contact information, you can email me and I'll send you to the right person. And I mentioned that we are recording this, and I'm going to try to post it to YouTube later. And the script that we're going to be covering is also going to be available in the SPEDAS distribution under the projects, MMS examples, and then webinars folder. And we have a bunch of other scripts in there from previous webinars. So I guess we can go ahead and jump in now. So the load routines all follow the same syntax of MMS _ load _ XXX, where XXX is the instrument you're interested in. So it's like MMS load FGM for the flux gate data, MMS load SCM for the search coil mag. And there's also MMS FSM, which is a data product of the that combines the FGM and SCM data, but and that's an L3 data product. But last time I checked, this is only available for team members, so you'll definitely need a password, a username and password to the SDC to get access to that at the moment. There's the EDP, that's the electric field data, ASPOC, it's the ASPOC data, EDI is the electron drift instrument, FEEPS is the Radii energetic particle sensor, that's the electron EPD instrument, and EIS, which is the energetic ion spectrometer, FPI is fast plasma investigation, HBCA, and then it's the hot plasma composition analyzer. And then there's ephemeris and coordinates, which is MEC, and DSP, which is the digital signal processor. One of them that's actually missing here is MMS load state, which is also ephemeris and coordinates, but provides access to the data through the ASCII files at the SDC. Save that. And these actually provide access to more recent data. I think the MEC data is delayed by 30 days. So if you want data in the past, say, month, you'll need to use MMS load state. And there's the digital signal processor, which is DSP, and we'll show pretty much almost all of these. And there's MMS load TQF, that's the tetrahedron quality factor. And then we also have MMS load burst segments and MMS load fast segments, which loads bars that allow you to show the data availability. So the burst segment bars and the fast segment bars. And all of these load routines load data using some standard keywords. And if you don't set the keywords, it defaults to essentially some standard defaults for all the instruments, with the exception of T range. If you don't set the time range, it'll ask you for your time range. It'll just prompt you for it. For For probe, it defaults to probe 1 for most instruments. I think FPI defaults to probe 3. Data rate, it usually defaults to survey mode or fast, depending on which instrument you're looking at. Because some call this fast survey mode fast, and some call it survey mode. And data type depends on the instrument. Level usually defaults to L2, but we also have the other levels like CITL and Quick Look and the L1B. But non-L2 data requires an MMS team member user and password to access those. And time clip. So the way the load routines work, if you when you load data, it tries to grab all of the data files that have essentially data within the time range you specified, which in some cases, it just, what it does is just dump all of the data from those CDFs into memory. And so in some cases, if you request a small time range, you can actually get more data than you actually requested. And to time clip the data down to the exact time range you want, you have to specify the time clip keyword. The reason we don't do this by default is because it could take a lot of time to actually time clip the data products. And I'll show examples of that. So there's an SPDF keyword, which tells the load routines to load the data from SPDF instead of the last SDC. And you just set it as a flag. And all the load routines also accept the tplot names keyword, which returns the names of the tplot variables that were loaded. So you just set it to an IDL variable like tnames, say tplot names equals tnames, and it'll return the variables that were loaded in that load routine call in this variable called tnames. And there's also a keyword available, which returns a list of files that are available at the SDC for your requested parameters. This won't actually download the data. This will tell the load routine, don't download the data, just print out which files are available. And it also prints out the total size. So this is useful if you want to make a load routine call for, say, many months of data, but you're not sure how much is actually going to be downloaded. You can set the available keyword, and it'll tell you which files are going to be downloaded and how big they are and how big the total is. Like if you wanted to load 3 months of HBCA data, which is very large files, it'll it should tell you the total size, which might tell you don't actually want to do that because of how big the files are. It could be several gigabytes worth of data. And another useful keyword is TT2000. And what this does is it preserves the TT2000 timestamps found in the CDF files. By default, all the load routines load the data and with the timestamps being in Unix times. But the conversion from TT2000 to Unix times can have precision issues. So if you want full nanosecond resolution, you have to set the TT2000 keyword to preserve those TT2000 timestamps. And one important note about this is that a lot of analysis routines in SPEDAS don't actually, they assume that you have Unix times in your data. So you really have to be careful when working with TT2000 times. And there's a crib sheet somewhere in the examples folder that talks about working with these TT2000 times if you're interested in trying that out. Okay. So, and there are many more keywords for the load routines. Some of the load routines have keywords that are specific to that instrument. So if you want a full example or you want a full list, just type .edit and the load routine name, and it should bring up the load routine. And right at the top, there's a list of all the instrument or the keywords that each load routine accepts. Like we have no update, which tells it the load routine not to go out to the SDC and download the data. It just only loads the data if it's stored locally. Another useful one is suffix. This will append a suffix to the end of the variable name, or all of the variable names. You can also set var format, and this will allow you to limit the CDF variables that are loaded into tplot variables. And this is really useful if you want to load data very quickly, and you know what the format of the variable names are of the variables you want, because most of the files have a whole lot of variables that you won't actually need to load. So you can say if you only wanted to load FGM data and SM coordinates, you can specify the SM variables using var format. I think I have an example in the webinar script. And there's also keywords for returning the list of CDF files that were used when loading the data, as well as controlling the CDF files and which versions are loaded, like setting a min version, a major version, only loading the latest version, and a specific version, which is CDF_version. And so if you're curious about trying out different keywords, just type edit MMS load and then the instrument you're interested in, and it'll it should be right at the top. And I should also note that there's going to be many more examples of the keyword usage in the crib sheets. These are just simple scripts that show how to load the data and do various things with the data. And it's projects, MMS, examples, and then basic and advanced. And there's also a webinars folder. And the thing to note is that some of the webinars might be out of date. We try to keep the basic and the advanced crib sheets up to date. That is, if something changes in the load routine, we'll update those crib sheets if they're affected. But the webinar scripts generally don't get updated after the webinar. So I guess we can go ahead and jump in and load some ephemeris data. And I mentioned earlier that this script, after this webinar, I'm going to post it into the webinars folder here, but it's not in there quite yet. So to get started, we're loading some MEC data. It's MMS ephemeris and coordinates. And I mentioned earlier that if you don't specify the probe keyword, it loads probe 1. But in this case, I'm loading all 4 probes. So I said probes equal to 1, 2, 3, and 4. And I set the time range to October 16th. So it starts at October 16th and ends at the end of October 16th. And I guess another thing to note is that this is the first element of T range is inclusive and the last is exclusive. So it really just goes to the very end of October 16th and doesn't go into October 17th at all. All right, and so now we have the data loaded. So if you want to create a plot of, let's say, position data and SM coordinates for all 4 probes, we just call tplot on the variables. One thing to note is that tplot accepts Unix style wildcards. So that means question mark matches a single character and stars match multiple characters. So when we call tplot and on this variable name, it should plot the data or the position data and SM coordinates for all the variables for all of the instruments, because I have a question mark where the probe number is. So let's go ahead and call that, and you can see, so it plotted the position data for all 4 spacecraft and SM coordinates. And you can see by the labels on the right-hand side here, the top is MMS1, then below that it's MMS2, and then MMS3, and MMS4. I'm about to show how to manipulate this plot and change the labels and the titles and everything. But first, if you want to list the variables that are loaded, there's a function called, or a procedure called tplot_names. So you just call tplot names, and it'll create a list of all of the variable names that are loaded in memory right now, as well as a number off to the left-hand side. You can refer to the variables names by their name or this number when calling tplot. So technically we could do like tplot 195, and that'll plot MMS4 position data. But let's go back to plot with all spacecraft. Another way to return those variable names is to use the tnames function. And this allows you to actually return the variable names in an IDL variable. So now we just call vars equals tnames, and vars should contain a list or an array of variable names now. So this is useful if you want to say just store all the variable names you currently have in an IDL variable. And for actually working with the data and pulling data out of these variables, you use get_data, and you give it the variable name. And the data keyword returns the actual data structure containing the data in an IDL data structure. The delimits keyword contains the default metadata, and the limits keyword returns metadata that's set by the user. So, and I'll show some examples here. So I'll get data, and I mentioned earlier that the time values are stored as Unix times, and those are stored in d.x. The y values are stored in d.y. So let's call help on d. You can see d.x. Those are the time values, and then the y values are d.y. So you could say d.x is for the first time. You see that's a Unix time, and d.y, and that's the first position, first point in the position at SM coordinates. And those are in kilometers. It should say by doing help. Actually, that's the next line. Call help. When I call help on DL, it shows the DL data structure, which has, you can see the Y subtitle has that it's in kilometers. Another thing to note is that the CDF metadata is stored in the DL, the delimits. So you can say help dl.cdf, and it has the CDF file name, the global attributes, the variable name, and the variable attributes. So you can say bat to get the CDF variable attributes. And the opposite of get data, so if you want to create a variable from IDL data structures, you call store data. So it's store_data, and then give it the variable name, and then you set the data variable or the data keyword and the delimits and limits. And of course, you can leave off the metadata and set these later using options, and I'll show examples of that. But if you want to take the same metadata from another variable that you extracted with get data, you can just set the same delimits and limits, and it should have the same metadata. So you can see when I called stored data, created a new variable called position_data, and we should be able to plot that by just calling tplot position data, and you can see created a new window. So another thing to note about the MMS and coordinates data is that some dates, I know some dates don't actually have the default data type. That is this one here. And if that data aren't available for your time range, try a different data type. And there's a note about this in the header of this load routine. And the difference between these is that these files actually have various variables that depend on the magnetic field model. And sometimes there are issues creating those variables using the Sega 04 model, which leads to these variables actually not being available. So if you set the data type to the 89D, these use the Sega 89 model. And those are generally available all the time. And this only really affects those variables that depend on the magnetic field model. So the position and velocity data should be the exact same across those different data types. And of course, to see all the data types, check the header, and it should have a list of the valid data types under the documentation for data type. And each one of those is essentially just using different field models, I believe. So, so in this load routine call, I reloaded the mech data and just using a different data type. And this is for only probe 1 because I didn't specify the probes here. The probes keyword, you can notice that it only changed MMS 1 data. And one useful routine when it comes to ephemeris data is converting kilometers to Earth radii. So you can do that without actually extracting the data from a tplot variable by just calling tkm2re. And just like the tplot keyword, this accepts Unix style wildcards. And a lot of the analysis routines that work on tplot variables actually accept Unix style keywords, just like the tplot routine procedure. So you can see it created 4 new variables, 1 for each spacecraft, and it appended a suffix _RE. So that's the position data in RE and SM coordinates. And this assumes this is the conversion to RE. And if you forget this, you can actually just open up this routine, and it's right here at the top, KM and RE. And so now we're gonna replot the data, and this time we're gonna plot it in RE. And I'm using both Unix style keywords in this example. So we match all MMS spacecraft with a question mark where the number is supposed to be, and then we use a star to match the RE. So now you can see create a plot, and it's MMS 1 on top, 2, 3, and then 4, and the y-axis is now in Earth radii. And it also updated internally the Y subtitle is no longer kilometers, it's now RE. So all the conversion and plot updates were handled internally. And to change various plot options on a panel, you use the options procedure. And so for the first example, we're going to change the labels. And these are the labels on the, it's actually supposed to be the right-hand side here. So that's these labels over here. So we're going to go ahead and change those, and you change them 1 variable at a time. So we changed MMS 1, 2, 3, and 4. We set the labels to X, Y, and Z. And another thing to notice, after you call options, it doesn't actually update the plot immediately. So you have to call tplot again to actually recreate the plot. And if you call tplot without any arguments, it replots the current plot with the most recent updates to the options. So just calling an empty tplot command, it updated you can see it updated the plots with X, Y, and Z. And for each of the panels. And by default, it puts the The labels are at the end of wherever the end of the that line is. So it tries to, sometimes it'll squish them together if the lines are close to each other on the right-hand side. So to change that, there's an option called lab flag, LAB flag. So you could set that to 0 to disable the labels entirely. Setting it to 1 spaces them out equally. -1 also does equally, but in reverse order. And 2 is the default. It'll put them just exactly like this at the end of the data point. And you can also set them according to the lab position keyword. So in this example, we're just going to set them placed equally, but in reverse order. So now they're placed, you can see on the right-hand side, they're placed equally in X, Y, and Z. But just as an example, we can set options to +1, and this should, and we're only going to change MMS1 and call tplot. And so you can see for MMS1, it's the X is at the bottom now, so it's X, Y, and Z. And so what about the left-hand side? And of course, this is backwards too. For the left-hand side, that's this title here. It's called Y title. And I mentioned earlier, this is Y subtitle. So if you want to change the Y title, you just use the Y title option. And so in this example, we're going to update the Y title to be MMS and then the spacecraft number and then position. And in this case, the bangs C stands for a new line. So it should drop the position down to the next line. And of course, I'm calling tplot after setting all these options to recreate the plot. So now you can see it as MMS1 and then position below it, and then it still has the Y subtitle. And just like we just updated Y title, you could also update, you could change the Y subtitle with the Y subtitle option. So it's like, just for an example, we could change the Y subtitle for MMS1 with Y subtitle equals, and call it subtitle. And then replot it, and you can see for MMS, the first panel here for MMS1, it updated the subtitle to just subtitle. So, and just like with options, there's also a thing that, or a procedure that allows you to update global plot options. So that's options for the entire figure rather than just a single panel. And that's tplot underscore options. So just for example, we're going to update the X margin and the character size to be the X margin to be 25 characters on the left and the right, and the character size to be 1.5 times the default character size. And we're also going to add a title to the figure called MMS position. And you can see it updated the X and Y, or the X margins. It increased the character size of the plot and added a title, MMS position, to the top. And important thing to note is that these options are essentially just the options available to the plot procedure. So all the options available to the plot procedure, you should be able to change with tplot underscore options. And there's a full list in the IDL documentation for the plot procedure. And they all generally follow the same format. So you can do Y margin, X character size to only update the X character sizes. So I would go to the IDL documentation if you're really interested in digging in to figure out how to update some kind of, or update something that isn't here. And you can get the current plot options with the get options keyword to tplot options. So So we called tplot options with the get options keyword set to opt, and then just called help on opt, and it shows the current options. And you can notice that in the bottom right-hand corner, there's a time step that tells exactly when this plot was created. So if you're creating publication quality plots for a paper, you might want to disable that that timestamp. To do that, you just call timestamp underscore or time underscore stamp, and then give it the off keyword, and then call tplot again to recreate the plot. And you can see now that timestamp in the bottom right hand corner is gone. And of course, timestamp with the on keyword should turn it back on. And if you want to save the current figure as a PNG file, so you just call make PNG and give it the file name. So we're going to create a file called MMS underscore position underscore data. And this saves this in your current working directory for IDL. So it created a PNG. Let's see, I should have that open. And here's the file just created. So it's the current plot as a PNG file. If you want a PostScript file, it's tprint. And again, you just give it the file name. And there's some options to tprint, like landscape. By default, it does the opposite of landscape. But these generally look better as landscape plots. So it created a .ps file. And you can see it's much higher quality. That's a PostScript file. And another useful ephemeris and coordinates routine is the MMS underscore orbit underscore plot. And this will create the orbit plots. And so you just give it a time range. So in this case, we're giving 6 hours on November 23rd, 2016. And it also accepts the keyword chord. And I think by default it uses GSM coordinates or GSC coordinates. But other options are ECI, GSM, GEO, SM. And so let's go ahead and create that plot. And internally, MMS orbit plot goes out and downloads or loads the data, the position data required, and then does all the work behind actually creating the plots. So right now it's loading the data, and now it's plotting it. And it's still plotting. For some reason, things take longer when other people are watching. Usually this is pretty fast. There we go. So it created the orbit plot for 6 hours of data. And it included all 4 spacecraft. And on the y-axis is the y position, on the x-axis is the x position. And if you look at the options, and there should be one for changing the plane. So you can change the orbital plane of the plot. By default, it's XY, but you can also do YZ and XZ. And you can specify other probes or only do one probe. And there's also an option to disable the image of the Earth and set the title. And this is based on some code that was written by the last people, and we just adapted it for SPEDAS. Another useful routine is the formation plots, and this is MMS mech formation plot. And then you give it your time, and it should create a formation plot of all 4 spacecraft at this specific time. Or what it actually does is find the time and the data closest to this time and uses that to create the figure. So it might not be exactly at 1306. It might be 1306 and few milliseconds, depending on where the actual timestamps are. So again, internally, what this does is go out and load the data for all 4 spacecraft and then create this formation plot with the tetrahedron. And just like most of the other load routines, this routine has a bunch of different options. So to see all the options, you have to open it and look at the header at the very top. And look at the keywords. One that you might be interested in is quality factor. If you set this, it loads the tetrahedron quality factor. It includes that at the top. And so there's a projection keyword that allows you to actually do the spacecraft, project the spacecraft position onto various planes. We could change the sun direction, set a rotation matrix, a general rotation matrix, an element rotation matrix to do to rotate the spacecraft positions prior to creating the plot. And then there are a bunch of keywords for plotting vectors on these as well. Like you can plot the B field at the center of the plot or plot the B field at each spacecraft location. So if you do the B field at the center of the plot, it does the average B field vector. And we'll just do an example with all of those. So in this next example, we give it a specific time. And we want to include the FPI, the DIS vector at the center of the plot and the DES vector at the center of the plot. This is the average velocity vector. And we also want to include the average B field at the center of the plot and then the spacecraft position projections onto the planes. And change the spacecraft size and set the sun direction to the left. And for these, we're also going to use set the data rate for FPI data. Instead of using the default of survey mode or fast survey mode, we use burst and the FGM data rate to burst as well. And another useful thing is is the normalization vectors. So it's a FPI normalization, which will normalize the vector to allows you to shrink the vector essentially to actually fit on the plot. And so internally, this will go out and grab the position data. It goes out and grabs the FPI data, the FGM data, and then creates the figure. It should be coming up soon. And I suggest checking both the header of the formation plot code here, as well as the formation crib sheet. There's a crib sheet that shows how to do all of these or create a bunch of formation plots. There's also examples in the header here under examples. And it shows an element transformation, XYZ transformation. All right, so it created the formation plot. You can see that the spacecraft positions are now projected on the various planes. That's because of the projection keyword we added. You can see the vectors are plotted and those are projected onto the planes as well. The FGM is the red, the green is DIS, the bulk velocity, and the blue is the DES bulk velocity. And this is an interactive plot, so you should be able to grab the corner and drag it to create or to enlarge it. And since it's interactive, you should be able to click or left click inside the figure and move your mouse around to actually be able to move the plot around. And we included so many options, it's going to be hard to actually figure out what's going on here without. So I suggest starting small by just creating a simple formation plot and then adding one at a time if you're confused about something that's in the plot. And another thing to note is that while in that example, we included all of the projections on all of the different planes, there's also, you can do only specific planes with, say, for example, XY projection, projects the spacecraft positions on the XY plane, XZ does the XZ plane, and the YZ projection does the YZ plane. And of course, the coord keyword allows you to change the coordinate system. And so for fields data, it's the same as with MEC data. It's just MMS_load FGM for FGM data. And so in this example, we're loading burst mode data, just a small amount of burst mode data. I think that's like 3 seconds of burst mode data for all 4 spacecraft. And we're using the time clip keyword to get exactly those 3 seconds of data. And then we're also going to load burst mode position data, which is MMS load MEC, and for the same 3 seconds. And again, all 4 probes, and we're setting the time clip keyword to get exactly those 3 seconds. And for this, we're also going to use the Var Format keyword and only load the GSE variables. So adding the Var Format keyword here should speed up the MMS load MEC call, since it's only going to be loading these variables that match this pattern. Should be the GSE variables. So you can see it loaded the FGM for all 4 spacecraft, and now it's loading the MEC data and GSE coordinates. Now it looks like it's time clipping them. And one thing to note is that we still have our tplot options set from before, and we had the title set to position, or MMS position. So I'm making a call to MMS, or to reset that title to empty the position out, since we're going to create a plot of the FGM data. So we don't want to have that old title there. So now we have the FGM data, and the title's gone, but all the other options are still there. The global options, you can tell the character size is still 1.5 times, and the X margins are still set to the same. And since we used the time clip, it should be only 3 seconds of data. So it gave us exactly the time range we wanted. And so one thing to, one important or useful tool is the Kerlometer calculations. So to do Kerlometer calculations with the FGM data and the position data, you just call MMS_curl, and you give it the time range, and then the fields variables. Those are the FGM variables in GSE coordinates, and the position variables in GSE coordinates. And one thing to note about the FGM data here, if we go tplot names, you can see that there are these variables that have, say, FGM B GSM, but don't have the BVEC at the end, the BVEC and the B total. These variables by default have the magnitude attached to the end. So if, for instance, we call get data on this variable called D and help on D, you can see it has 4 components rather than 3 components that a vector should have. That's because the magnitude is attached to the end. And by default, when you load FGM data, it splits, it creates new variables, one called BVEC, or ends in BVEC, which actually has just the variable or just the vector, and then B total, which has just the magnitude. And so in this case, where we created this plot here, I plotted the variables that have the end in BVEC, so it only included the vectors there. And so that's also those are also the variables we're going to use in MMS curl for the Kerlometer calculations. So just quick, just called MMS curl, gave it the time range and the fields variables and the position variables. And these have to be in GSC coordinates for these calculations to work. So you give it the GSC variables, and you can see it created some more variables with different, with the actual Kerlometer calculations. Like it has J total, it's the total current calculated, and the parallel and the perpendicular currents. So we're going to go ahead and add up the J total variable to our current plot. And I haven't mentioned this yet, but to add a new panel to the T-plot window, to your current T-plot window, you just use the add keyword and then give it the variable name. So in this example, it's going to add the current calculated using the Kerlometer calculations to the top. So without the add keyword, it would have just plotted the current. But since we used the add keyword, it just added it to the top of the current plot. And so for more examples with Kerlometer calculations, there's a crib sheet. I'm not sure if it's in the basic or advanced folders. We also have another routine that's that uses a very similar, essentially it's another Kerlometer calculation provided by a different scientist, but it produces the same results. And so there should be examples for using both or either in the crib sheet for Kerlometer calculations. And just like for FGM data, you can load the SCM data using just MMS load SCM. So in this case, we're going to load 3 hours on October 16, 2015. We're going to load survey mode, and we're going to use time clip to exactly those 3 hours. And that's the first 3 hours. And since these data files are daily, so you can see by the file name that this is just one day. This is the full day of October 16th. If we hadn't used the time clip keyword, it would have loaded this full file and would have loaded the full day's worth of data, even though we requested the T range end at 3 hours after. And that's that issue. We just don't time clip by default because it can take some time. You can see here, time clip, spent clipping the variables, it took almost 2 seconds. So now we can plot the SCM data in survey mode. And a useful routine for working with this SCM data is TD power spec. This is the dynamic power spectra, and the T just stands for T-plot variables. So this calculates the power spectra using this SCM data. And I set some options here. The options that I used here actually came from the SCM team, and they have various defaults for these options stored in the crib sheet. So if you're using burst mode SCM data, these options are probably going to be different. So I suggest checking the SCM crib sheet for the options when you calculate dynamic power spectra. But yeah, I just took these from the SCM crib sheet, which was created by the team. And you can see it created 3 new variables. That's the dynamic power spectra for each component. So you can see X dynamic power spectra, Y dynamic power spectra, and Z. Of course, we can create T-plot names and see the last 3 variables created were those dynamic power spectra. And so we can, right now we just have a plot with the SCM data. We can add these dynamic power spectra with a T-plot and then add, and then just give it a variable name that matches all of these, which should be these last 3 variables. And so you can see we have the X component on top, the Y component in the middle, and then the Z component. And then since we used the add keyword, it just added these variables to the plot, to the current plot. And of course, you can use Y title options and set the Y title to fix the default Y title here. I think by default it's using the variable name as the Y title. So another useful routine is to highlight a time interval in a panel. There's a routine or procedure called highlight underscore time interval, and you just give it the variable name and then the time interval that you want to highlight, and then a color, the color option. So in this example, I think it's coloring it yellow. And then once you call this highlight time interval, you have to call tplot again to recreate the plot with the highlighted time interval. So you can see 130 to 150 has been highlighted now in that panel. And we can load EDP data, this MMS underscore load EDP. And by default, this loads the DC electric field data. But in this case, we're setting the data type to SCPOT and DCE. So it's going to load the electric field data as well as the spacecraft potential. So the spacecraft potential are stored in the electric field files. And you just set the data type to SCPOT to load those variables as well. So we can call tplot names. You see the last variables loaded were the spacecraft potential and the DC electric field. You can go ahead and create that figure. And so we have the spacecraft potential on top, and then the GSC coordinate, or the electric field and GSC coordinates on the bottom. And another useful routine for working with tplot windows is time bar. This allows you to add vertical and horizontal bars to a panel. So in the next example, we're going to add a horizontal line just at 0 to the EDP panel. Notice right now it doesn't have any, there's no line at 0, but if we call time bar, give it the data value 0, and you also have to, by default, it uses a vertical line, but if you set the data bar keyword, it does a horizontal line. So now we have a horizontal line at 0, and accepts various other options like thickness and line style. We set the line style to 5, so it's dashed. And in the next example, we're going to set vertical bars and set the thickness to 3, so they're going to be thicker. I have the default line style just a straight line, so we added 2 vertical bars. So this is, in addition to highlight time interval, it's just useful for setting, just adding ranges to current tplot windows. And of course, we also have the electron drift instrument, which is just EDI. So it's MMS load EDI. And that loaded pretty quick. So then you call, and since we didn't set the probes keyword, it loaded probe 1 just by default again, and it loaded survey mode. But again, you can set data rate keyword probes, see the header of the routine for all the options it accepts. Notice it accepts burst, fast, slow, and survey mode, and the default is survey. And so in the next, we're going to go ahead and plot that data. Where one of the variables is the E cross V drift velocity and GSC coordinates. So we just use that variable and plot it. And so now we have the EDI drift velocity, or the E cross V drift velocity plotted in GSC coordinates from the EDI instrument. And then there's also the digital signal processor, that's DSP, which is MMS load DSP. In this case, we're setting the data type to EPSD and BPSD. That's the magnetic power spectral density and the electric power spectral density. And we set the data rate to fast and the level to L2. And we're also going to time clip it. I don't think we don't actually need to use the time clip keyword here, since these are probably, these are daily files. And just like with the other load routines, you can open this and look at the header for the available options and the defaults. And so we loaded those data, and we can go ahead and create those. So the EPSD is the electric power spectral densities on top, and the magnetic power spectral densities on the bottom. You can see there's something going on here with the bottom of this plot. So if you want to set the Y range to eliminate this noise down here at the bottom, you just use Y limit and give it the variable name, then the start and the stop. So we're just going to update that and then call tplot to recreate the plot. You see now it updated the Y range. And there's also a Z lim, which allows you to update the color bar range as well. And another option, by default, it uses, it's going to use log scale, but if you give it a 0 at the end, it'll change the Y limit to linear scale. So now you can see that this bottom panel is on a linear scale. And if you give it 1, it's going to be back to log scale. I think I have to recall tplot. Oh, oops, spelled that. So now it's back to a log scale. And so there are lots of useful crib sheets for fields data. Some of the probably more interesting ones are, say, coordinate transformations, like the MMS QCotrans crib, shows how to do various coordinate transformations with MMS QCotrans. There's MMS Cotrans LMN crib, which shows how to do LMN transformations. That's in the advanced folder. There's an example showing how to calculate the pointing flux, also in the advanced folder. And there's a crib sheet showing how to do minimum variance analysis coordinates, also in the advanced folder. And of course, each load routine also has its own crib sheet. So if you want to dig in further, I suggest going through the various crib sheets. And we could probably show some of those just as examples here. So for the basic folder, we have lots of crib sheets here, you can see. And for advanced, we have even more. And so I guess we can move on to EPD. So it's FEEPS and EIS. Let's go ahead and load some electron data. So that's MMS load FEEPS, and then set the data type to electron. And since FEEPS is mostly electron instrument, the default data type is electron. So if you didn't specify this, it loads the exact same data. Same thing with survey. You don't actually have to set the data rate to survey. By default, it loads the survey mode data. And although you can also load ion data for FEEPS. And so if you wanted to load ion data, you have to specify data type equals ion. And in this example, we're going to load data for probe 4 instead of 1, since we've been mostly working with probe 1. Just show that you can specify probe as probe 4. And so one important thing to note is that for FEEPS, we do a bunch of post-processing calculations. After we load the data from the data files, we actually calculate the omnidirectional intensity as well as count rates. And we also spin average it by default. So just like the other load routines, you can open the FEEPS load routine and look at the options at the top. But you can also look at the code to see all the post-processing that happens after loading the data. So we have various corrections to the energies in the files. The ions have the flat field corrections applied. We remove bad data for the bad eyes and bad energy channels. And these are all from the team. We also have only use active eyes, certain active eyes. And by default, when you load the FEEPS data from the CDF files, each sensor head has an extra data value at the end that's at the integral channel. We split that out into its own variable. We remove the sunlight contamination, and then we calculate the omnidirectional spectra, and then we calculate the spin averages, and then we create a smooth data product. And you can actually use the num smooth keyword to change that, and I think that's in seconds. Yeah, so set this keyword to create a smooth omnidirectional spectra, and smooth equals 1 for 1 second. And setting num smooth to 19 should produce the same as the spin average, or very close to spin average, since it's 19-second spin period. And that's why loading the FEEPS data can actually take a little while, because we're doing all those extra calculations after actually loading the data. I guess while it's still loading, we can look at some of the keywords. Like there's the keyword ignore telescopes, which tells you to ignore specific telescopes. And if you do this, I suggest talking to the team about the telescopes that are included, and whether or not ignoring specific telescopes in the omnidirectional spectrograms is a good idea for the time range you're interested in. And another thing to note is the data type here depends on the level of data you're looking at. So for L2 and L1B data, the data types are electron and ion, but for L1A data, it's electron and then the sensor, which is bottom, top. And so now the data are loaded, and you can see we can call tplot names to see the last two variables created were the omnidirectional spectra and the spin average omnidirectional spectra. So I called tplot on those. So it should have the omnidirectional on top and then the spin average on the bottom. And so omnidirectional on top and then spin average on the bottom. And a really useful routine is this routine called Flattened Spectra. This allows you to create a plot of, in this case, intensity versus energy at a specific time. So if you just call Flattened Spectra without any options, what it does is allow you to pick a time on the plot to essentially flatten the spectra for that time. So I'm just gonna pick a time here, just say around 2 o'clock. So like that, and you can see I found the time closest to 2 o'clock, and it created intensity versus energy for that time. And the legend has the just black variable is the regular omnidirectional spectra, and the blue variable is the spin average omnidirectional spectra. And I'll show some examples of how to change these legends in a second. There are lots of options to the flattened spectra routine. So one of them is replot. So what this does is recreates the plot with new options. So you can set X log, Y log, PNG to actually create a PNG file. And you give it the file name to create, to tell it what the file name should be. And if you use the replot keyword, it'll use your previous time, so you don't actually have to select the same time. So this should recreate that plot, but this time the x-axis is on a log scale and the y-axis is on a log scale, and it should have created a PNG in our called Spectra in our IDL working directory. has the spectra. And PostScript also works, so you can create a PostScript file here, trying to create a publication quality plot. And if you know the exact time, or you know the time, instead of clicking on it, you can also specify just a time keyword. So in this example, instead of clicking on the plot or on the figure, we just call it with the time keyword, and it should set the same, or set the same. And a thing to note is that you don't actually have to know the exact time. It'll find the time in the data closest to whatever time you specify. Another option is the bar keyword, and this will creates the same plot, but in this case, if you look at the figure, it has a vertical bar at the time that you specified. So just like with all the other routines, opening it and looking at the header, you should see all the available options. Though it looks like the bar keyword isn't actually here yet. So I'm gonna have to update the documentation here to add the bar keyword. Interesting. I didn't know that was missing. But you can see you can specify the X, Y, and C, or X, Y range. You can disable the legend, change the colors, set a file name prefix, set the file name specifically, give it the time, set a time range to average over a specific time range, use a number of samples to average over a specific number of samples, give it a time window, just a length in seconds over which to average. And I'll show you some more examples soon. But first, let's calculate the pitch angle distributions for FEEPs. So by default, we don't have pitch angle distribution data. So you have to actually calculate them by calling MMS underscore FEEPs underscore pad, and then you give it the probe number. And of course, you have to call this after you already loaded the FEEPs data. And by default, it uses electron data. So if you loaded ion data, you have to actually specify data type equals ion. And internally, this just grabs the data and then calculates the pitch angle distributions. And this code was provided by the team. And just like with the load routine, there's a num smooth that allows you to create a smooth data product as well. And a bin size allows you to set the size of the bins. I think in this case, we just use the default. So call tplot names again, look at the variables created. See there's pad, which is the pitch angle distribution, non-spin averaged, and there's smooth, which is the smooth. I'm not sure what the default smoothing is, so go check pad. It's like, yeah, so it looks like it's smooth. There's 1 second smoothing by default on that. And then there's also, it creates the spin averaged pitch angle distribution. And of course, there's an energy keyword that allows you to change the energy range. By default, it should be the full energy range. And so now we have at the top, we have the non-spin average, non-smooth, just regular pitch angle distribution. In the middle, we have the 1 second smooth pitch angle distribution. And then at the bottom, it's the spin averaged pitch angle distribution. And EIS is very similar. This is the energetic ion spectrometer. It's just MMS load EIS. And in this case, we're loading survey mode EXTOF. That's the energy by time of flight data. And then the pH by TOF. That's the pulse height by time of flight data. And again, we're using probe 4 just to mix things up in survey mode. And if you're wondering about the data types, again, you just open open the routine and look at the header, and it should tell you the available data types. and the available data rates. And just like with FEEPs, when you load the EAS data, there's some post-processing that happens. It's actually not as much as for FEEPs, but it does do spin averaging and then calculates omnidirectional spectrograms. And I think by default, it loads the energy by time of flight data. So if you didn't specify the data type keyword here, it would load the energy by time of flight data. But since we did specify it, it's loading both energy by time of flight and pulse height by time of flight. And you can call tplot names. The last few variables should be the all of the EAS data. So you have the omnidirectional here. That's omnidirectional proton. And just go ahead and plot here. So what we're doing is creating a plot of the energy by time of flight proton flux that's spin averaged. You should be able to figure all that out from just the variable name. And so there's this other routine, just like with flattened spectra, we have flattened spectra _ multi, which allows you to create a plot of multiple times. So this allows you to flatten the spectra at, say, when I give it 3, it's 3 different times. So it'll allow you to, say, click 3 times. So there's 1, 2, and then 3. You can see the legend names now has the time that the spectra was created at. And since I didn't say X log or Y log, it just did it on a linear scale. But as before, you can set the time keyword to specific to tell it to create the spectra at specific times. And in this case, we are going to set the X log and the Y log keyword just to show. So this time we didn't actually have to set we didn't have to click the plot. It just used the time keyword, the times available. And the black is the at 6 o'clock, the blue is at 7, and then the green is at 8. And just like with FEEPs, we have MMS EAS pad, which calculates the EAS pitch angle distribution. And again, this was provided by the team. So it uses your previously loaded EIS data to create the pitch angle distribution. And again, you can open the routine and look at the header. One useful thing that the EIS team does is add changes. They will keep a revision history at the top of their routines that shows the recent changes or all the changes. And again, you can specify the pitch angle bend size, set the energy keyword to limit the energy range. And there are some more useful options. But I suggest talking to the team before venturing off into the other options, because some of these options are experimental and they're still working on the routine. All right, so we can again call tplot names, see what the variables were created. So you can see there's regular pitch angle distribution variables, and then spin averaged, again, which is the suffix applied spin, and for different energy ranges. And the one we're really interested in is the full energy range, which is 44. This is energy by time of flight data, 44 through 979 keV. And so just like with the load routine, if you don't specify a data type, it defaults to energy by time of flight and proton data, since it's a ion spectrometer. You can change the data type to pulse height by time of flight to calculate the pulse height by time of flight pitch angle distribution. But in this case, we just use the defaults and set probe 4. And so we're going to create. So if we call tplot on that spin averaged variable, it should be the pitch angle distribution for the full energy range and energy by time of flight proton flux. I think if you call it without the spin suffix, it should create the non-spin averaged variable. And we'll probably, for the example here, we'll use the spin average variable. So I showed earlier that flattened spectra and flattened spectra multi work on energy spectrograms. They also work on pitch angle distributions. So we call flattened spectra multi and set it for 3 times and do y log. It actually creates the pitch angle distribution at these specific times. You can see the angles are on the bottom, 0 to 180, and then the I think it's the flux is on the y-axis. And again, 6 o'clock is black, blue is 7, and then 8 o'clock is green. And of course, the y-axis is on a log scale since we set the y log keyword. I guess we could move on to FPI now for the plasma data. So just like the other instruments, it's MMS load FPI. And so for the plasma data, there's a really important keyword here, center measurement. For all the other instruments, the data when they're loaded are already at the center of the accumulation interval. But for FPI and HBCA, that's not true. For FPI and HBCA, when you load the data, they're actually at the beginning of the accumulation interval. So when you load FPI data and HBCA data, you have to set the center measurement keyword. And what that does is shift the data points to the center of the accumulation interval. And this is especially true if you're going to be comparing, say, or plotting FPI data and FGM data at the same on the same figure. That's because you really need those the data to be shifted to the center of the accumulation interval. Otherwise, you're going to be plotting apples and oranges. So in this example, we plotted the error bars, which are created on the fly, and the number density for DES, and then the error bars or the error flags for DIS and the number density. So what this does is shows where there are potential problems with the data and what those problems might be. So that's useful for really digging in. And just like with pretty much everything else, there's crib sheets that show all of this. More examples of the crib sheets. So another useful thing with tplot, and I get this question a lot, is how do you add error bars to a tplot variable? I think FPI is a good example for here because they actually have error bars on their number density. So in this case, what you do is call get data, and then on your number density, and then get data on the error bars, which are called error right after number density. And for this particular case, I'm multiplying the error data by 100 so that you can actually see them on the plot. It's supposed to be 100, not 1,000. Otherwise, if you create the error bars with just the error in the variable, it's actually really hard to see for this time. And then you call store data and you give it the variable name. And just as before, the X component is the times, so it's just the same d.x. The Y component are the Y values, which is just d.y. And then for the error bars, it's dy, and you give it the error data. And then we're using the same metadata from the initial variable. So same t limits, the same limits. And we call tplot names. The last variable created should be DIS density with errors. So let's see, way down here, DIS density with errors. And then we can call tplot on that variable. And so you can't actually see it because it's plotting the whole day's worth of data. So you'll have to zoom into the plot to actually see the error bars. So in this case, we're going to zoom into 5 minutes of data here. So now you can see that we had the lines, we had the line with the number density, but also each data point has vertical error bars added. And again, if we didn't multiply this by 100, it would be 100 times smaller and much more difficult to see. So I just did this multiplication by 100 to show that the error bars are, so that the error bars actually show up on the plot. And another thing to note is for t-limit, if you call t-limit without giving it an argument, it allows you to select 2 times on the plot on your current figure to zoom into. But since in this case, I knew exactly what times I wanted to zoom into, so I just set it as an option. If you want to reset the time range, you just give it the full keyword and it resets to the full time range. Again, I can go call t-limit without any options, and it actually allows me to select times on the plot. So we can select some times around 1600. And again, t-limit full resets to the full time range. And there are more options in that procedure at the top. So you can do the last plot limits, which is last. You can zoom in by a value between 0 and 1. So there's lots of options here on that. But the most useful is just giving it the T range that you want to zoom into, and then using full to go back to the full time range. And so I guess we can go ahead and load some HPCA data. So it's just like with all the other instruments, it's MMS load HPCA. And just like with FPI, you have to use the center measurement keyword. Otherwise, the data loaded are going to be at the beginning of the accumulation interval. So it's good to just remember to add that there. And by default, it's going to load the moments data. But in this load routine call, we're specifying ion data and the moments data. So ion is the spectrogram data. And we're also going to time clip it, and we're going to request 1 hour worth of data. And again, for probe 4. And an important thing to note about the HPCA ion spectrograms, that is the data loaded with the ion data type, is that these, when they're stored in the CDF files, they have the full angular data with them. So they're not actually, they don't have omnidirectional spectrograms by default. So you have to call some of these routines below to actually create the omnidirectional spectrograms from the variables that are loaded. So to create the omnidirectional spectrograms, you have to call MMS HPCA calc A nodes and give it the field of view. By default, it's going to use 0 to 360, but I wanted to specify it explicitly here just to make it clear. And then you have to call MMS HPCA spin sum to do a spin sum, or essentially the sum the values over the full spin. And that's required for the omnidirectional spectrogram for HPCA. The spin sum routine accepts the keyword average AVG. So this will do a spin average instead of a spin sum. So if I didn't specify the AVG keyword here, it would just sum over the full spin rather than averaging over the spin. And for all the available options, just like the other routines, you open the load routine, or open the routine, and then check the header. So you can specify certain A nodes to sum or average over, or you can specify a specific field of view, like you can do 0 to 180 rather than 0 to 360 to only look in a certain direction. And by default, it's going to use it's going to do all of the probes currently loaded. And I don't think there are too many options in the spin sum routine, but just to show, there's a field of view, and then you can, so if you specify the field of view in the calc A nodes routine, you also have to specify a field of view in the spin sum routine so that it knows which variables to use. And again, averages instead of sums. And after we do this, we're going to create a plot showing the DIS omnidirectional spectra that were loaded when we called this MMS load FPI, as well as the HBCA flux that we are calculating up here. That's the omnidirectional flux. And we're also going to plot the EIS pulse height by time of flight proton flux and the EIS energy by time of flight proton flux. We're going to plot all of those on the same figure. But an important thing to note is that these all have different units in different places. So I'm going to, so for instance, I think the y-axis is going to be different in different units, and as well as the color bar is probably going to have different units. So I'll show that as soon as it creates the plot. And it's probably worth opening HBCA load routine and showing the header here. So the just as before for the data type here with HBCA, the available data types depend on the level. For L2 data, it's ion and moments. But if you're loading L1B or CITL data, there are different data types like the flux and the moments, and the RF corrected data. And of course, if you're looking at this data, you'll need a username and password to the SDC, and you'll probably need to talk to the team about the data products that you're interested in. And an extra keyword for HBCA is disable Mem Usage. So if you try to load too much data, you can use way too much memory, and it'll essentially crash IDL. So internally, it actually checks if you're approaching your memory usage and warns you. And you can disable that with the disable Mem Usage keyword. And while this is also still loading, I should point out that there's all the load routines except a keyword called always prompt. This tells the load routine to always prompt you for your username and password. By default, when you first load the data, it'll prompt you for a username and password, and you can just save an empty username and password to access the public data. But if you accidentally type something else in there that's not valid, and it complains that there's an invalid user password, you can set the always prompt keyword to any of the load routines, and it'll always prompt you for your username and password. HBCA data takes a long time to load. So I guess while that's still loading, we can show the next example with flattened spectra, or at least talk about it. There are a couple keywords that I didn't show earlier called 2flux and 2keV. Since when you create this figure with different the energy spectra from different instruments, and they have different units, you can actually, when you flatten the spectra, you can by default, it'll just create the plot or with the units of the spectra or units of the spectra in the plot. But if you give it the 2flux keyword, it'll convert the spectra to flux before actually creating the flattened spectra. And if you do 2keV, it'll convert the Y values to keV before creating the spectrogram. So we can open flattened spectra, see those. And it just uses for the 2keV, it just uses the units in the Y subtitle. And for 2flux, it uses the units from the Z title. That's the color bar title. And the reason this is useful is because I think the FPI data here is going to be in EV, and pretty sure the EIS data is going to be in KEV. And I forget which units HBCA is in. I think it's going to be KEV. So if you just call flattened spectra without the 2keV, one of the variables would be in KEV and one of the variables would be in EV, which isn't very helpful. And with 2flux, some of them are intensity or energy flux, and some of them are just in regular flux. So again, you really want to convert them before creating a figure. And this took a lot less time yesterday when I was running for some reason it takes a lot more time whenever I show this to other people. But another thing to note, I mentioned earlier that you can change the legend names on these flattened spectra figures. So for instance, here we have the omnidirectional spectra and the spin average spectra. To change the legend name here, you just set the legend _ name option. So in this case, for the pulse height by time of flight, we could set it to EIS pulse height by time of flight, and that would update these legend names, or the legend name for this particular variable to always show EIS pulse height by time of flight. And then here would be energy by time of flight. And I'll show that once the data are loaded. And I guess while we're loading that, we can show some of the other crib sheets. So in the basic crib sheet folder, or examples examples basic, you can see we have a crib sheet showing how to find burst intervals. So this will show you how to add a panel to the plot that shows a bar wherever there are burst intervals. We have EIS angle crib sheet. This allows you to create angle plots at various energies for EIS data. So there's a crib sheet for the FPI response and flags. This was provided by Barbara. This essentially shows you how to create those plots with the error flag bars and what they mean. And there's FPI angle, which allows you to create FPI angle plots, and HBCA angle. Same thing for HBCA. And there's a crib sheet that shows how to add version numbers. That's the CDF version numbers to your plots. So you can actually keep track of, and let's see if it opens. So yeah, so this allows you to set the versions keyword to actually keep track of the version numbers of the CDF, and then you add those to the, you can add those to the current figure. And there's a crib sheet that shows how to save the data to ASCII files. So it's just MMS save to ASCII. There's one for the orbit plots and one for state data. This is the ephemeris data. It's loaded from the ASCII files, the large ASCII files. Let's see. And let's see, there's a plasma beta crib, and this shows how to load or how to calculate plasma beta using FGM and FPI data. So it includes the conversions required to actually calculate them and how to calculate them. And this is useful also because it shows usage of calc, which allows you to do calculations with tplot variables without actually using get data and store data. So you can do various calculations with calc. It also is a useful crib sheet for showing how to interpolate. So in this case, we interpolate the B magnitude to the number density timestamps. So that's just T interpol. And let's see. Most of those. Oh yeah, this is the Flattened Spectra crib. This shows examples just like we've been using with Flattened Spectra. And it includes PostScript examples and Flattened Spectra multi, and how to use how to convert the y-axis to flux. And this is all just in the basic folder. There's also a MMS Config. This allows you to set MMS configuration settings, like where your local data directory is stored. It also allows you to set, shows how to set up a mirror data directory. So the difference between a mirror and the local data dir is, say if you're at Swery, I know they have a local mirror of the data stored on the network. And so you can set mirror data directory to your local network mirror, and it'll load the data from there instead of the SDC, but you have to use node download to do that. And this is useful because instead of just setting your local data directory to your mirror, the mirror data directory, well, if this is set, it'll actually download the data from the mirror to your local data directory. And because if you're trying to load large files over the network, it'll actually, it'll take a lot longer. So if you have a local mirror on a network, you'll probably want to set mirror data dir. Let's see. And again, there's the Kerlometer crib sheet. I showed the MMS curl example earlier. That's the first example in here. There's also this MMS Lindergrest. I think MMS curl was provided by Jonathan Eastwood and Ty Fan, yeah. And this other MMS Lindergrest was, let's see. This is still loading. It's definitely taking a lot longer than it did yesterday. So for the advanced cribs, I mentioned earlier we have LMN transformations. There's a basic dayside crib sheet, a tail crib sheet. Looks like this might actually be finished. Nope, still going. And these were provided by the team. There's also MMS event search, which allows you to search for events in the database, the events database. So it's just MMS event search. And I suggest just going through the script sheet to try it out if you're interested in that. And one thing that we didn't show was wave polarization. You can do that with the SCM data. There's a crib sheet specifically for that. So you just load the SCM data. And then there's lots of examples here for calculating the wave polarization, doing those calculations. And it's actually getting close now. So let's go back to the webinar script, because right now what's happening is that it's doing these spin sums or spin averages. I can tell because it's creating variables that end in underscore spin. So it should be almost done, finally. And we probably shouldn't have time clipped the HBCA data, because you can see here, time spent time clipping the data took 859 seconds just to time clip the data. So that's a good example of why we don't time clip the data by default. All right, so it finished. We created the, so call it tplot names to see the variables it created. So now last variables, you can see these are just the summed over the A nodes, and then the ones that end in spin are the full omnidirectional spectra for the different species. So H plus, HE plus, HE plus plus, and then the O plus for the oxygen. So now we can finally create that plot that shows the FPI at the top. This is the ions from FPI, then H plus from HBCA, and then the EIS should be the pulse height by time of flight data in the middle, and then the energy by time of flight data at the bottom. And then since those are here, let's go back and show that the units on each of these plots are different. You can see that this is an EV, the HBCA is also an EV, and the EIS data are in KEV. So if you want to call flattened spectra, you actually have to use those 2 flux and 2 KEV options to do that conversion internally. And so now you can see the on the x-axis, all the data are in KEV. On the y-axis, they're all in flux. And so the X, or the black is DIS from FPI. The blue is the HBCA H plus flux. Green is pulse height by time of flight from EIS, and the red is energy by time of flight for EIS. You can see they cover different energy ranges. And just as I mentioned earlier, you can call options and set the legend name to change the legend names. And so now the legends has been updated, so it's just FPI, DIS, HBCA, and then pulse height by time of flight, energy by time of flight for EIS. And another useful tool is tplot underscore multi-axis. This allows you to plot, create a figure where one panel has 2 different axes, one on the left and one on the right. So the top panel here, you can see what I call tplot multi-axis. It created this figure with the top plot with the DES number density. It's using the left-hand axis, and the DES temperature is on the right-hand axis, so an EV, but they're on the same panel. And to do that, you just, the first set of arguments is just the plot for the left-hand axis, and then the right-hand plot is the second argument. And then you have to give it a number for which panel to put the right-hand plot over. So in this example, we're just saying put the temperature over the first plot in the multi-axis. And this also allows you to create line plots over spectra. So in this example, we create the density, velocity, and then energy spectra for DES on the bottom. And then we plot the DES temperature or perpendicular temperature over the omnidirectional energy spectra for DES. You can see the energies for the energy spectra on the left-hand axis, but on the right-hand axis, you have the temperature. And it's hard to see because the back is blue, but the temperature is actually overplotted there, the electron temperature. And again, we specified 3, so it puts the perpendicular temperature over the third panel, which is the energy spectra. And I'm not sure if we're going to make it through all of these examples, since we only have about 10 minutes left. But there's also routines for calculating the energy spectra from the distribution functions directly. So that would be MMS part get spec, and there's a crib sheet. I should show the crib sheet. So it's MMS part get spec, and then MMS part get spec advanced crib. And the advanced one shows more advanced usage. So if you're interested in this, I suggest checking out the crib sheets. And what this does is calculate the energy spectra directly from and the pitch angle distribution directly from the distribution functions. And by default, if you don't specify an instrument, it does HBCA or FPI. And so if you want to load HBCA or do the calculations for HBCA, you have to specify the instrument equals HBCA. And internally, you don't actually have to have the data loaded to call this. Internally, it actually goes out and loads both the distribution data as well as any support data required to do the calculations. And this is a very powerful tool. So I definitely suggest, in addition to the crib sheets, taking a look at the header, because you can do the energy spectra, you can do pitch angle distribution, you can also do gyrophase spectra, just the theta spectra, the phi spectra, and there's examples showing how to do pitch angle distributions at each energy. And this is very useful for quickly doing various energy range or different pitch angle ranges or energy. And there's also moments. You can do calculate the moments directly from the distribution functions. So it's like the density and the velocity. And subtract the bulk velocity. You can subtract the error, subtract the spin tone, and do photoelectron corrections for the FPI electrons. So in addition to checking out the header here, you definitely want to go through some of the examples if you're interested in this. Some of the examples available in the crib sheets. And so here's the normal crib sheet. And so the regular crib sheet for MMS part get spec shows how to use how to set various energy ranges to limit the calculation to various energy ranges. It also shows how to use multi-pad to actually create different pitch angle distributions. And it has both FPI and HBCA examples. And one important thing to note is that these MMS part get spec only works with HBCA and FPI. The EPD instruments aren't included yet because they don't have distribution functions released in their CDFs. And another useful routine is 2D slices of the distribution functions. So that's MMS part slice 2D. And again, by default, I think it uses FPI data. So if you want to do HBCA, you have to do set instrument HBCA. And just like with the get spec, I suggest taking a look at the crib sheet in the advanced folder. It's MMS slice 2D FPI for FPI and HBCA for HBCA. And there's way more examples in here. You can do set various rotations for field align rotations. You can set averages, set the time window. And by default, again, just like with MMS part get spec, what this does is go out and loads all the data, loads all the support data for you. And so you should be able to create 2D slices just with a single call to MMS part slice 2D. We even have examples for subtracting the bulk velocity and subtracting the error in the FBI data. And there's various rotations I mentioned for field align rotations. And finally, we're probably not going to be able to get to this one either, but there's this routine called MMS Flipbookify. This allows you to combine these 2D slices with a current T-plot window. So you create a T-plot window just as you would before, and then you call MMS Flipbookify, and it'll actually go out and calculate the slices and add them to your T-plot window. And then it creates a figure for each time. And if you specify the video keyword, it actually creates a video. And so again, I suggest taking a look at the MMS Flipbook crib in advanced for that. We're definitely not going to have time to get to that, but it shows how to load the data, create a T-plot window, and then just call MMS Flipbookify. And it saves the output as PNGs or PostScript files, and or a video if you want a video. And just like the other routines, check the header for a list of all of the available options. And I actually have a video I created yesterday when I ran through this of one of these flipbook. So this is the video created with this example here. You can see we have, here, I'll show you so we plot the number density, the ion number density for FPI, the ion bulk velocity for FPI, and then the ion energy spectra. And then when we call Flipbookify, it adds the ion slices at each data point. And since I requested a video, it created this video. You can see at each data or each point, it created the slices. And by default, it uses 3 different rotations, which is VX, VY, VX, VC, and then VY, VC. But this is like pretty much everything else. This is configurable internally. And you'll have to check the header and the crib sheet for options. But it's you can change these planes with the slices keyword, so you can do field align slices as well. And another thing to notice that with the slice, the time at which the slices are taken is actually represented by a dashed bar. And since I specified the T range keyword here, it only did a very limited time range, only 20 minutes. And it actually specified those 20 minutes as vertical bars, solid bars. And I think the meeting is probably about to end since I only set it for 2 hours. So I guess we should probably end it here. And I will go ahead and add this to the SPEDAS distribution, the latest bleeding edge. And so I'll add this script, and it'll be located here: projects, MMS, examples, webinars, and then MMS analysis webinar. And I'm going to try to upload this to YouTube either today or tomorrow, depending on how long it takes to convert. So this script should be available by tomorrow, and the video should be available by tomorrow. And if you're looking for the video on YouTube, it's just I suggest Googling YouTube SPEDAS. I think it's just youtube.com/SPEDAS, but I usually just Google it. All right, I guess should probably end it now before it ends it for us. So thanks for calling in. And again, feel free to email me afterwards if you have any questions. It's egrimes@igpp.ucla.edu. And my email is also in the analysis or in the announcement email. So thanks again.